full screen.
Yeah, it's good. Control L, usually.
No. Sorry.
That's it.
Is this okay now?
It's perfect.
Okay, good.
Okay, and we are streaming now. Control L, usually.
Sorry.
Okay, so should we start?
Mm-hmm.
Okay, so let me introduce Yunfeng Jiang
Yeah.
from University of Kansas, sorry, who's going to talk about Vafa-Witten invariants and S-duality. Thank you very much for giving this talk. It's your floor.
Yeah. Thank you so much, Maria, for the invitation. Very good, right? Long talk. I haven't given online talk for a long time after the COVID, I guess. So yeah, so I will talk about the I guess this is a long time project that we're already doing, the Vafa-Witten theory and the S-duality. And although I recently I spent a lot of time doing some other things like, maybe you heard about that, the general type surfaces, KSBA modular space, and the virtual class. I hope this is related later. And I haven't have very many new stuff on Vafa-Witten theory for some time. But anyway, I will talk about what I got in the past, I guess, already 6 or 7 years, right? Or 6 years. So I give some interesting background, but I guess the audience, right, probably you are more better than me for this physics, I guess. But I just, give motivation because online talk give some background. So the motivation for this is kind of n equal to 4 supersymmetric Yang-Mills theory on 4 manifold, right? So in physics, we already know that the S-duality is a strong weak duality and maybe related to the, I guess it should be, right? Related to the mirror symmetry. And in mathematics side, it should be related to Vafa-Witten theory and, some other Tanaka-Thomas theory. We will see that this S-duality, what we define the invariant, will be Tanaka-Thomas invariant, okay? And also, so where this come from? This is from the classical Maxwell theory, which gauge group is a C star, right? U1, and the electromagnetic duality. Okay, so this is the electromagnetic field duality, Maxwell equation, PDE, which I'm not very familiar with PDE, but anyway, this is the duality. And then you will see here there are some, the physics terms, right? E is the electric field, B is the magnetic field, T is the time, and C is the speed of light. And then this Yang-Mills theory is a generalization of the one-dimensional gauge group to the, non-commutative gauge group, SU2, SU3, and so on, SUR. And we will see that we will mainly, at the moment, I will work on the SUR gauge group, okay? Of course, this is in the quantum field theory, the electromagnetic field, unified into a single entity called the electromagnetic field. This is the, really is one of the Yang-Mills gauge theory. Okay, so in the gauge theory, we in physics study the symmetry, right, of the groups. Like we are mathematicians, we understand this math, and the S-duality was given by I guess 1970. I forgot the time anyway, by Mortonen and Olive duality, which is the special type of this Yang-Mills theory. Okay, for us in the mathematics, I just fix two Lie groups. This as we should fix the Lie groups, right? Like U1 and SU2, or the algebraic reductive group in the algebraic geometry sense or number series sense. So in mathematics, suppose we have a 4-manifold M, and the G will be a gauge group, and the LG will be the Lang-Lang-Stuhl group. Okay, so this is really a math term now. And the Lang-Lang-Stuhl G and the LG means any reductive group we have the root system, right? You take the root system and then you take the dual root system and then find the corresponding group called LG. So this is really a duality, which is very popular and important recently in the number theory called the Lang-Lang's correspondence. And maybe also, I guess you heard about the geometric Lang-Lang's correspondence. Okay. So the duality is given by G to LG, which in physics, in the theory, they said that they count the partition function of the G or LG instantons in physics. And in mathematics, we know that in 1994, we followed the Vafa-Witten's proposal, and they consider the G equal to SUR and LG equal to SUR mod R. So this is really a long do group, right? An example, a very important example, actually, in even in number theory. For example, in number theory, you have G or LG, you have the very classical. This is a two classical group, right? You have the classical group GLR, the long do still GLR, SUR, SUR mod R, right? And for example, you have some other like the simplex group and correspond to SO 2n plus 1, and the G2, the long do is G2 group. So which I know that these several examples. And here we have a very interesting example. For example, if G equal to SU2 when R equal to 2, right? And you will see that the long-do is SU2 mod D2, which is SO3 because SU2 is the double cover, right, of SO3. So that SU2 will be simply kinetic, but SO3, the fundamental group is Z2, right? Z mod 2Z. So this is really very interesting two groups, which already important in number theory and also in physics. But now here, for us, I'm doing the enumerative geometry, right? So S-duality here means if I take, in algebraic geometry world, I take M is the algebraic surface S, means over C is two-dimensional, over R is the real four manifold, okay? We actually, let's make a notation, ZSURQ, this is the partition function of SUR instantons. And SUR mod DR will be the partition function of SUR mod DR instantons. And then we will make this rigorous in mathematical sense, okay? And here Q equal to E 2 pi I tau. Tau is the parameter of the up half plane. Here tau in physics means this, okay, which I don't understand. Maybe you guys some can understand this. And this theta G are coupling constant. Theta is theta angle. G is coupling constant, which this is in the quantum field, right? In Yang-Mills gauge theory, it's really called the electromagnetic field. Okay, so this is has some physics meaning. This tau, and in our case, I would like to let Q equal to E 2 pi I tau. We count Q as a parameter in the generating function. Okay, so in mathematics, in physics, Vafa-Witten in 1994, their paper in nuclear physics, they studied this S-duality conjecture for this four manifold. They said they predicted, like we said they predicted, right, a mathematician, but in physics, they obviously this is already true, right? This is here. But as you are partition function, when you invert tau to -1 over tau, so then we'll have the following functional equation, like the generating function of SUR will related to the generating function of SUR mod ZR like this. Here, chi is the Euler characteristic of the surface S or the four manifold. If you think about the group SL2Z, right, and the determinant one integer matrices, 2 by 2 matrices, and then you can see let a subgroup gamma 04 equal to this subgroup, this contain these matrices, satisfy 4 divide C, and you can do this similarly for gamma 02 means 2 divide C, okay? S-duality means this. And we know that any point, any element, 2 by 2 matrix ABCD in SL2Z acts on the up half plane by this formula, tau to this A tau plus B over T tau plus D. And the group actually SL2Z is generated by two elements, S and T, okay? Here, S, we really call the S-duality. I'm not sure if this S coming from this. Let's assume yes, okay? So because it's S, send the tau to -1 over tau, and tau, and the T actually send the tau to tau plus 1, it's a shift. And the gamma 04 is actually generated by T and ST4S, and the gamma 02T similarly. Gamma 02, sorry. The S-duality means the generating function of SURQ is a modular form with modular group gamma 04 or gamma 02 if M is the spin manifold. Okay. Moreover, sorry, I see more. Moreover, when you apply tau to minus 1 over tau means the S transformation, this one, then you will get this formula, like in the left side. So this is the whole S-duality conjecture, I guess. Okay. So if you want to check or prove this S-duality conjecture in mathematics, we need to find the rigorous mathematical definition of the was SUR is theta and was SUR modular is theta. What does that mean, right? As in mathematical sense, and then prove what I said, this formula. Okay. Actually, people studied this for a long time, even go back to the Donaldson invariant, which in algebraic geometry sense is the polynomial invariant of modular space of stable sheaves on the surface S. So, but that one, I think that there are some progress on that to, I guess one of the, probably one of the direction there at the moment, maybe in 1990s, right? This is to understand S-duality, right? Using Donaldson invariant. At least some mathematician did a lot of work there. But it turns out that this is not the correct, probably not the correct definition, only recently. So recently, around 2017 or 18, I guess, and Tanaka-Thomas, right, Richard Thomas, they found the kind of correct definition for this S-duality invariant called the Vafa-Witten invariant. So I will review what's that in mathematics. So they defined the left side, what I mentioned here, the ZSURQ. What's that in mathematical sense? So this is coming from the modular space, so-called modular space Higgs bundles, which Marina is working on, right? So working on modular curves. But now we are in the situation of algebraic surfaces. So for this, let's fix a smooth projective surface S with polarization H. Okay, so ample divisor. And E is a torsion-free coherent sheaf on S. And then we can define the Hilbert polynomial, right, with respect to the polarization. And you can use this Hilbert polynomial, take a reduced Hilbert polynomial to define the stability, so-called Gaussian stability. So here it's in the right side. I don't want to, repeat this. Maybe people are already familiar with this, right? And at the same time, we can define the slope stability, right? But here we use the Gaussian stability to define the moduli, okay? And here is a very known, fact, right? Slope stability is much stronger. Is the most strongest, right? But the slope semistable is the most weakest. Okay? And then if you have the stability, you can define the modular space of stable or Gaussian stable torsion-free sheaves on S with a fixed invariant chain classes C, means you fix C0, which is the rank. Sorry, not C0, sorry, CH0, okay? Take a chain character of the sheaf. CH0 is the rank, and the CH1, CH2 related to the first chain class of second chain class of the torsion-free sheaf, right? And here we also even do further. We want to fix the determinant so that fixed determinant means our structure group of our bundle, because I fix the determinant L, then the structure of the torsion-free sheaf or vector bundle will become SLR, suppose the ranks are. Okay, so that's why we fix the determinant, because we want to study the Langlands-Lu group later. Remember, I mentioned that SUR correspond to SUR modular, but in algebraic geometry sense, in the moduli, the structure group will become SLR, so that the Langlands-Lu of SLR will be PGLR. Later we will see. Okay, yeah. So for this, we can define the modular space of these stable sheaves. So this is the, I guess, this is the modular space of only stable sheaves or semi-stable sheaf. But this is not the correct thing. We will do Higgs later. But before we do that, I will at the same time introduce another modular space, the so-called modular space on surface Deligne-Monfort stacks. So really, you need to think more, algebraic surfaces I call the Deligne-Monfort surfaces. Okay, that means you have some singularity, or before singularity. So here, for this project, for today, right, I only need a so-called eta gerb over surfaces. What that mean? This means the following. Maybe if you are not very familiar with the, Deligne-Monfort stack or stack language, maybe a little bit like. But if you're familiar with the stack language, I think this is okay, right? So if I fix an abelian group A, now my abelian group can be infinite and can be finite. Okay, mainly we will talk about A will be C star or cyclic group of order R, mu R. Okay, these two cases. An A gerb over a surface S is a smooth Deligne-Monfort stack curl S. And usually, if you have a Deligne-Monfort stack curl S, and then S will be the cosmodular space of this Deligne-Monfort stack. And the examples of the gerb, for example, the mu R gerb is on P2. For example, I can take P2 cross mu R, which is the trivial mu R gerb. Like mu R globally acts on P2 trivial. Okay. And if you want to have a non-trivial gerb, take a line bundle on P2, which is non-trivial. Let's take O1 on P2, and then delete the zero section, and give the C star action on the fiber given by the weight R action, right? Lambda go to lambda power R, lambda power R, lambda power R action. Then the quotient, stack quotient, will be the weighted projective stack PRRR. This is a non-trivial mu R gerb determined by the line bundle, non-trivial line bundle. Okay, this is the examples. So a mu R gerb curl S twisted sheaf is actually a coherent sheaf such that the mu R action on E is given by lambda power 1. So really, you can think, probably we know that what's the twisted sheaf, but for me, right? If I have a Deligne-Monfort stack gerb, the gerb twisted sheaf is just a subcategory of the category of sheaves on the Deligne-Monfort stack, because the coherent sheaf on the Deligne-Monfort stack curl S, right? You can have any mu R action. The weight can be lambda 1, lambda 2, lambda 3, and so on, right? But now I only take lambda 1 action. So if the sheaf like this, we call twisted sheaf. Okay. And so any question about this?
Yeah, one question, sorry. What is the lambda 1 action here in this case, for the gerb?
Because you have a mu R, you have a mu R gerb means locally around S, you take an open cover of S, UI, for example, and then locally looked like UI cross mu R, right? Cross B mu R.
Yeah.
That means the mu R acts trivially on the on the open subset of S. Am I right? But if you have the sheaf on the gerb, that means the mu R acts on the sheaf can be non-trivially. So I only want all my sheaf. I have the action can be diagonalized. The diagonal action always lambda 1 x, lambda 2 y, and so on, like the rank.
Okay.
So the action is given by lambda power 1. There's no splition. Does this make sense now?
Okay, yeah, I think it makes more sense now.
You
Thanks.
you can split the the mu R action like mu R act like lambda 1, lambda 2. Then you can split the lambda 1, lambda 2 means the eigenvalues, means the eigenvalue of the mu R action. I always like the eigenvalue correspond to 1. E 2 pi I 1 over R. Is that okay? This is the eigenvalue. Yeah. So this is a very special, not very special, but anyway, this is a subcategory in the category of coherent sheaves in the Deligne-Monfort stack curl S. This I call the twisted sheaf. Yes.
Sorry, so every coherent sheaf on that stack has a natural action from that
mu R,
basically?
Yes.
Okay.
So this is a definition actually of the stack of the coherent sheaf. So now for this, you can define the same thing for the Hilbert polynomial of this gerb, and everything is very similar. And then you can define the classical stability for the twisted sheaves and define the moduli. So I let MCL twist, TW means twist, curl S, be the modular space of stable gerb, this gerb twisted torsion-free sheaves with K group C belong to the K0 group, the group-centric K0. So, and this I fix the determinant means also I need the structure group will be SLR if the ranks are. This is very similar. Okay, so this is a tool like before we go to Higgs. So we can define modular stable or semi-stable, gaseous stable or semi-stable sheaf on the algebraic surface with fixed polarization. And at the same time, I can define the modular space of gerb twisted if I have a mu-r gerb over the surface. Okay, now let's go to the Higgs. So as I said, around 2017 and 18, Tanaka-Thomas, they defined the so-called Vafa-Witten invariant, which is the correct invariant for the Vafa-Witten theory, for the S-duality at the moment. And how they define this? Let's review their construction, but I will do at the same time both for the gerb and the surface. You will see if the gerb is trivial, that's the surface, okay? Now, suppose capital X, this curve X equal to the total space of the canonical line bundle of the gerb of the surface, you can think. And if the surface, the total space of canonical line bundle will be the Calabi-Yau threefold, right? So here is a Calabi-Yau threefold stack, DM stack. And then pi is the projection. And from spectral construction, we will have the following equivalence. The modular space, the Higgs bundles or Higgs sheaves on the surface or on the gerb will be equivalent to a compactly supported two-dimensional sheaves on the total space of the canonical line bundle. So that is E phi is a Higgs bundle. Okay, now what the Higgs bundle means, I didn't write down detail, means E is a bundle on the gerb or S, right? And the phi is E to E tensor chi S is a section. Remember, here I use canonical line bundle as the twisting, as the Higgs field, right? This map. So this is the same as in the curl case. For example, if your S, your curl S is a curl, then this is the same as the Higgs bundle the people working on, I think Marina working on. And in the surface case, you can still use the cotangent bundle. Remember, in the curl case, the cotangent bundle is the same thing as the canonical line bundle, but in the surface case, no, right? Here I use the canonical line bundle. I am not using the cotangent bundle. So the cotangent bundle is really the same percent Higgs bundle in the surface. But that one is more complicated, which we don't know at the moment how to do that. Okay. Now we use the canonical line bundle, and you will see that this is really a Calabi-Yau threefold theory. And the stability you can define at the same time, and you can define the modular space NLTW perp will be the modular space of stable Higgs bundles, this gerb twisted Higgs bundle actually, with invariant C, fixed determinant L. And I also want trace free, means the Higgs field has trace free. So this is really correspond to the SLR, still correspond to the structure group of SLR. Okay, so this is really, as I said, this is really a Calabi-Yau condenser. That's why Calabi and the Yau's pictures here, right? This is really a Calabi-Yau structure. So this total space of the canonical line bundle on S is a Calabi-Yau. But although it's open, right? It's not compact Calabi-Yau, it's an open Calabi-Yau. But in the Calabi-Yau case, this is threefold. So that the deformation theory and the obstruction theory of this modular space NLTW perp is actually locally controlled by the XT group, XT11 EE or XT2 EE, where E is the universal sheaf on there. So this is really the Calabi-Yau picture. And also you can show, because Calabi-Yau, the dual landing sheaf is trivial, right? And by serial duality, this EST1 EE will be isomorphic to the EST2 EE dual. So this is the serial duality. And you will see that this deformation is isomorphic to the dual of the obstruction, and the ESD2 is the obstruction. Okay. And this is really the symmetric perfect obstruction theory case by K-Barron. Okay. So that in the Tanaka-Thomas theory, you can define the invariant, the Tanaka-Thomas. So we can define the invariant using localization here first. And also we can use K-Barron's VWL characteristic. This is two invariant. We call big VW and the small VW. One is by localization, because you have a C-star action. The C-star action will scaling the Higgs field, only acts on the Higgs field, E5 phi. And the fixed point locus will be compact. And it's interesting to figure out the fixed point locus, right? We don't have so much time, but anyway. So this one will be related in a Tanaka-Thomas paper. They call the Higgs branch, not Higgs branch, called the instant branch and the monopole branch. Instant branch is really the modular stable shape. It means look, here, if I consider the pairs, right, E phi as a Higgs pair, so I can define the stability called this pair stability, okay? Only consider the phi invariant subshifts on E to define stability. So that means in this case, there exists situation so that E is not stable, even not semi-stable, but plus phi, E phi will be stable. So this kind of Higgs shift really happens on the monopole branch. Okay, this is very similar to the case in the modular space of stable Higgs bundle on curl case. Okay, on curl case, you will have the so-called cotangent bundle of the modular stable bundle on curl and some other branch, and also relate to the nilpotent cone. Okay, so this is a very interesting, I think, comparison, but which the nilpotent cone in the curl case, in the modular space Higgs on curl, take a very important role. Okay, for example, I think in the entroscopic decomposition stuff, they take a very important role. But here, in the modular surface case, this thing haven't largely explored yet, I think. Okay, so this is a comparison to the modular curl case. Now, in this case, for the SUR case, Tanaka-Thomas defined this invariant like this. And for the twisted thing, for the twisted shift, me and Ma-Tao Ku, we define the twisted Vafa-Witten invariant using the similar picture. Okay, but we define this for SUR modular, and I will mention later. Okay, so S-duality means the following, but I write down here as this, but maybe this conjecture should be modified at the moment. Okay, so if I have an algebraic surface, then my SUR modular invariant, for the SUR invariant, you can just sum over the Vafa-Witten theory as the, you fix R, fix C1, and then moving the C2, right? Then you can define the generating function of the Vafa-Witten invariant, SUR, maybe already did by Tanaka-Thomas. How to define the SUR modular invariant? So now we have a proposal with Ma-Tao Ku. We define this using the twisted Vafa-Witten invariant, really twisted. Okay, I will tell you exactly where later on why this is true. Okay, so this is SUR modular means, in roughly speaking, we need to sum over all the H2 S mu R, which classify all the mu R gerbs over S. I guess this one has something in physics. I forgot the name, what they call. Okay, and give some coefficient and summing over for each gerb, you count the Vafa-Witten invariant, twisted Vafa we define, and then summing over all of these Vafa-Witten invariant for all the classes in H2 S mu R. And then this is roughly, this is the SUR modular Vafa-Witten invariant. And also we conjecture that this one will match the S-duality conjecture in the beginning. Okay. So now let's do why this is true, right? Actually, in my original paper, I proved this. First, check this for P2, because for P2, you really need to check P2. For P2 case, this is the final case. There's no multiple branch, which only has instant branch, means any modular Higgs bundle on P2 will must be the corresponding sheaf or bundle must be stable. Okay, this one probably I can skip this, because this one's from a formal calculation with Martin-Ku and Gulampu, we did the modular stable sheaf, torsion-free sheaves on the rigid projective planes. We did a lot of calculation long time ago when I was a postdoc in Imperial. And then we got a lot of formulas. And then I really just realized that this formula can help to check the S-duality for P2. First, this routine check, right? Not that hard, and to check really, this is really true, and I match the prediction in Vafa-Witten's 1994 paper, because in the Vafa-Witten's paper they did several predictions, one for P2, another for case 3, another for general type. Let's move to the this is the formula for the P2. Okay, I just show the formula here. This is really a routine check, so nothing hard there. Okay.
I have one question. This Q to the 15/4. I mean, it's a funny number. Why 15?
Which one?
In the first formula, and just I'm surprised that you have a fraction there.
Oh,
and also,
yeah.
I mean, yeah,
I
don't know.
see. I don't know this. Actually, I don't know this number actually coming from. I forgot. But this is really in. Let's see. I think this is really also in Vafa-Witten, 1994. I guess.
I see. So it doesn't have any.
Oh, no.
I mean, any meaning. I mean, in a way.
Oh, so sorry. Maybe I'm wrong. Oh, maybe this one's in our case, in the P222 case. Probably this one will be related to some quadratic function thing. I forgot. Yeah. Something like that.
Okay, I see. Thank you very much.
Yeah, but anyway, this is a long time calculation. I forgot this. Yes, you are right. Probably related to some quadratic function thing, like the divide, what they call the formula, right? Give you modularity stuff. Yeah. Anyway.
Thank you.
Yeah. I think the interesting case is case 3 surface, which let's talk about that. So in the case 3, so the next case in the Vafa-Witten's paper, they predict this case 3. So for case 3 case, you will see that not all you will see the really how interesting thing is this. Let S be a case 3. We know that H2S case 3 mu2 is, let's only consider rank 2, okay? All the prime rank will be okay. So this Z2 power 22, so the rank is 22, Z2 power 22. And Tanaka-Thomas already calculate this any R can be any R, not only equal to 2, okay? Any R, SUR Vafa-Witten invariant with rank R, chain class, first chain class 0, and moving second chain class. So this is the formula, which looks very nice. Eta Q is the dedicated eta function. You will see this is a modular form. Okay. And how about another side? We can ask, what's the SUR modular, right? What's the formula? We can calculate for any prime rank R. Let's only focus on R equal to 2. If R equal to 2, as then any prime R should be okay. So in rank 2 case, we can first write down Tanaka-Thomas formula like this. So this is really the Tanaka-Thomas formula in the right side here. So this eta Q, now I let a new notation GQ equal to eta Q minus 24. So that I match the notation in the Vafa-Witten's paper. Vafa-Witten used capital G, right? So after S transformation, tau to minus 1 over tau, we can check this formula becomes the following. So this formula here is really the formula in Vafa-Witten's paper, 1994. We can take a look at that paper in nuclear physics. It's very interesting. And when I first look at this formula, I didn't know where this coming from, right? This 2 power 21, for example, 2 power 10, where this coming from? So this is a very, and in a SU2 case, you don't have that number, but here you have this number, right? Big number, 2 power 21. So actually for me, I first understand where this 2 power 21 coming from, actually. And then this project, it was studied, many years. I think in 2019, right, I proved this in almost early 2020. And this 2 power 21, you can guess, is really coming from this, right? Look, coming from the 2 power 22, right? You know, how many elements in H2S mu2. So I first realized this, and then I relate this one to the, you know, to the Gerber case. So that's why we solve this conjecture. And you know, you will see that in the S equal to K3 case, I first using my former formula. If I use my former formula here, this, and then I can calculate the SUR mod DR or SU2 mod D2 like this. The formula is this. It means you sum all the mu2 Gerbers, the Vafa-Witten formula. And the interesting thing here is, I didn't write here, but the interesting thing here is this. The classification of the mu2 Gerbers on the K3 surface S, there are two classes, big two classes, actually three classes. First class is the trivial Gerber, just trivial. Okay, trivial means S modular mu2 global S trivial. The second class is coming from the not trivial, but a little bit trivial, means I call the essential trivial. Essential trivial means the Gerber coming from a non-trivial line bundle on the K3 surface S, as I did the P222 before. Okay, so essential trivial and the trivial Gerber, they cannot give any new Vafa-Witten invariant. Their Vafa-Witten invariant is the same as Tanaka-Thomas. You can prove this. But there are some mu2 Gerbers so that their corresponding broad class is non-trivial. I cannot write, but I just say, okay, you can, from the exact sequence, you can map H2S mu R or mu2 goes to H2S OS star torsion part. So H2S OS star torsion, which is by definition the homological broad group, which is the broad group. The broad group is the group of isomorphic classes of Azumaya algebras, which is originally coming from the, I guess, coming from the field extension thing in number theory. This is still a very interesting conjecture. The so-called pure index conjecture means if you have a non-trivial Gerb, right? The Gerb, the broad class means the Gerb in H2S OS star, means this is an OS star Gerb, C star Gerb. So this Gerb, the period means the order, as a torsion group, they have order, finite order. And the index means the locally free twisted sheaf, the minimum rank. So the conjecture said there is a conjecture for the surface case is the period equal to index, which was proved by the Yunfeng first. And then later on, there are a lot of other proof by twisted sheaf, using twisted sheaf method by Leibniz, for example. And even now, I think in the high dimensional, for high dimensional varieties, the function field, the pure index conjecture is still open. Some cases approved, still widely open. So for me, I only use the surface result, which is true by the Jung. So this pure index conjecture pure index theorem, at least here for surface, take a very important role for the S-duality conjecture. Okay, so this, if pure equal to index, like this is the Vafa-Witten invariant correspond to the non-trivial broad class twisted sheaf. In this case, in the mu2 case, the minimal locally free rank, the minimum rank of a locally free twisted sheaf must be rank 2. There's no rank 1 for this case. So this is really the non-commutative analog of the Hilbert scheme. You can think of this. If the corresponding mu2 Gerber is a broad class non-trivial, then the twisted modular space of twisted sheaf is like the modular space of Azumaya algebras. Okay. So because Azumaya algebra is non-commutative. Okay. So in this case, you really need to calculate this non-trivial broad class twisted Vafa-Witten invariant, which we did before. Me and Martin with Martin. So this is you can think of this is the new contribution or the new finding in the SUR mod DR side, which is important. Otherwise, you cannot prove the S-duality conjecture in mathematical sense. Okay. So here in the right side, the S-duality for the K3 surface is really like this in the Vafa-Witten's paper. So in Vafa-Witten's paper, actually for this H2S mu2, right? You actually have and as I said, there from the lattice theory, they have three classes of classes: the trivial classes, they have the even classes, and the odd classes. And you can calculate how many even, how many odd. For me, for even classes, I use essential trivial gerbers, and for odd classes, I use optimal gerber called the broad class non-trivial gerber. We call optimal gerber. Okay. And we use the notion from Leibniz's definition. So then for this, you can sum it over the new formula for this in the right side. Then we can prove that really this is the, oh, sorry, I have a typo. This 2 power, sorry, this 2 power rho s minus should be 2 power 10, sorry. So this is really the Vafa-Witten's prediction or conjecture in the Vafa-Witten's paper. You can prove using the, I guess you can prove using this twisted thing. Okay. And if this rank 2 is, this any prime rank is okay. Okay, we prove this with Matang. So this is the S-duality conjecture for category. Any questions?
Go on, I guess.
Okay, very good. So now, actually recently we have a little bit of progress for singular category surfaces, but I just want to mention this a little bit. So for example, if you have S given by Z2 action, which will be called so-called the Nicolan involution, right? And this has fixed point, 8 isolated fixed point. My two students, they calculate this generating function. So look, this is very good. So this also match. And actually you can do more on the any S given by the AD group actions. Okay, there's a classification of the category surface given by a finite group action, which the action by is symplectically. Okay, and then there's totally 82 cases. Very interesting. Okay, and actually the formula can be calculated on the SUR side, all the 82 cases, but on the SUR modular side, I think we only can do maybe cyclic group at the moment because this really very difficult to check the S-duality. So this really, I don't know. Anyway, but this, for example, if you have a category surface given by action which is non-symplectic and sorry, my English, symplectic, right? So for example, you even have an involution. You even can have a Z2 action on the category surface S, which is not symplectic. And then you will have the fixed point locus. Maybe it's a curve. But in the symplectic case, all the fixed points are isolated. So in the non-symplectic actions, things are more hard. But things are more hard and interesting. But to my knowledge, at the moment, we don't know any Vafa-Witten generating function formula for non-symplectic action. So, for example, if you have a S modular Z2, right, which is non-symplectic action, so that the quotient is a rational surface, rational elliptic surface, maybe, or maybe rational surface, then we don't know how to calculate. This is not that easy, probably. If the audience has any idea for that, that will be very, interesting to see. And in another side, in the general type, as I said, Vafa-Witten actually predicted 3 cases. If I remember correctly, 3 cases in their paper. P2, case 3, we proved, and the account of some other general type surfaces. I think some other general type surfaces are very interesting. The formulas in their paper is 5.38 or 5.41, which is very complicated. We cannot prove at the moment. Okay, but in Jiang work with Brie, which is Matang student, and Gulampu, and with Matang, we proved actually for some general type surfaces. For any general type surface, the twisted Vafa-Witten invariant is deformation invariant. We can prove this. And also for class of general type surfaces, which satisfy some tonality thing, okay? The twisted Vafa-Witten invariant by a non-trivial broad class can be calculated by a general Tanaka-Thomas Vafa-Witten invariant. Okay, so this is what we get. I guess this result is a recent result, which we finished in last year or 2 years ago, only recent result. So now the situation in the S-duality conjecture is this, in a Vafa-Witten situation. For some general types of which is very most open case, right? We don't know how to prove the S-duality conjecture, but we can relate it or reduce the calculation of the twisted Vafa-Witten invariant SUR modular to the SUR side. Really, right now the situation is, or the question is, how to calculate the SUR side Vafa-Witten invariant, means the Tanaka-Thomas thing. This is the hard part. I guess Martin and Gaucher has a lot of conjectures for their rank 2, rank 3, rank 4, and so on, right? They have a lot of conjectures, but I don't know how many are approved yet. Probably some are approved. And if there are any good, but anyway, I heard from Martin that they can do the rank 2 case, but I'm not sure. So this is the situation right now. Okay, any questions?
I guess that there is no recursivity that can be thought for this for the computations, I guess.
Oh, you mean at the moment, right?
Yes, yeah.
Yeah, you're right. Probably it's I think it's not easy in the calculation. Yeah, but they can do some calculation, but cannot fully maybe solve the S-duality conjecture. But the rank 2 case, it seems Martin mentioned probably he can do using Joyce 1,000 pages paper or something like that. But anyway, I cannot follow Joyce anymore because his paper too long. So anyway, yeah. Okay, now I use I think yeah, almost. I use the last maybe several minutes or 5 minutes to talk about some other things. Okay, some direction, So the first diagram tells us that I learned from physics, but I'm not sure how to do that. It seems what I did right now the SUR modular theory is a SO3 minus theory probably, if I remember correctly. I remember I saw some physics paper of Douglas, I forgot. There exists some other SO3 plus theory, because SO3 is really SU2 module Z2, which I don't know how to do another theory. Okay, they said there is a T-duality between SO3 minus and SO3 plus, which I also don't know what that means in mathematics.
I think it's the orientation, right? Maybe.
Oh, really? I don't know. Okay, but anyway,
I think you
mentioned
can
this.
read it in the Tanaka and on the Thomas paper. They might write something about it.
Oh, maybe, yeah.
Maybe.
Yeah,
Could be.
Maybe the first one not that interesting, but anyway, I just listed it. So now the next, I in my mind, I have a long time picture in my mind called the so-called another situation, so-called Kapstein-Witten program. So this is really the geometry Langlands correspondence, which in their paper Kapstein-Witten in 2006, right? They call the geometry Langlands correspondence and the modular heating system, something like that. So in that case, they really talk about how to relate the S-duality to the Langlands duality. This is really, in my understanding, is how to relate this four-dimensional. I did the S-duality is a 4D supersymmetric Yang-Mills theory, right? How to relate this 4D case to the 2D case. 2D means the modular of stable Higgs bound on curves, I guess. If I'm correct me, please, if I'm wrong. So. But there, the program, maybe many people know, right? A lot of mathematicians are interested in this. But for example, in this situation, in my situation, I studied how to relate these two, which I don't know how to do at the moment. I don't think there's any result in this direction about this. And for example, if you can relate to the geometry Lambda to the modular of Higgs bound on curve, probably you can relate it, this S-duality to the so-called P equal W, P equal C, for example, recently, which is hot subject by Jian and Malik and their program, their group. So they did the P equal W or P equal C or some other Hassel-Satyas conjecture, which is proved several years ago means if you have a modular stable Higgs bundle, SLR, for example, and then you have a modular PGLR Higgs bundle, right? Then on the curve case, the modular PGLR Higgs bundle is the modular SLR Higgs bundle modular the gamma group, right? The pK 2 torsion, or pK R torsion, which is a finite abelian group. But this is not true in the surface case. But there is some relation maybe. And the Hasso-Zedius conjecture said the string, the Hodge number of the modular stable SRR Higgs bundle equal to the string Hodge number of the modular PGLR Higgs bundle, which is proved. But how to relate this one, or how is, and also look at the decomposition, right? I only familiar with Molik-Shen's proof for this Hasso-Zedius conjecture. They use the so-called entroscopic decomposition from Oh's fundamental lemma. So this entroscopic decomposition, it seems to me, is very similar to the S-duality decomposition, but different, of course. But for me, how to relate these two, I think is very interesting. At least I don't know how to do that. Okay, anyway, I stop here. I think that's all. Thank you so much.
Thank you.
Now, should I stop share or something? Or
Thank you very much. Thank you very much. Let me